Hello and good evening, and welcome back to my house, where I'm going to talk to you about math, because that's what people do when it's 8:30 at night and they're just wondering what they should be doing with their lives. Today, we're getting into some really exciting material. We're going to get into the basics of calculus, specifically dealing with slopes. And so what I'm going to be doing in this pre-calculus class is spending the next 2 weeks trying to give you guys the very, very, very basics of calculus and how calculus works. Now, calculus obviously is complicated enough to have 4 classes devoted to it at a minimum. And so you should not expect to understand everything perfectly at the end of 2 weeks of pre-calculus calc material. What I'm trying to do is expose you to it to make it so that if you ever see these concepts again, they're not quite as foreign to you. And for those of you who might have me next year, you'll be far more comfortable with the material having been exposed at least a little bit to it. So the first thing we're going to do is talk about the idea of an average slope. Now, if I told you that this graph right here that I've drawn with my slick art skills represented the position of somebody, they'd be running pretty fast, somebody traveling over a span of time. At point 1, or at time 1, they're at 20 meters, and at time 2, 3, 4, they're at 40 meters. The question would be, what is their average rate of change? Well, if I wanted to find the average rate of change, the average rate of change is just the rate at which this changes, dependent on the rate at which this changes. So the rate, or that rate, would just be my change in y, which is going to be 40 minus 20 over 4 minus 1, which would give me 20 over 3, which I guess isn't that fast. It's certainly feasible for somebody to run that fast. So we have 20 over 3 meters per second. Now, does that mean that this person is always running at 20 over 3 meters per second? Not necessarily. All we know is that their average rate of change was that. But in this case, because I've drawn a straight line, we could say that at any given point within this space, the instantaneous rate of change is 20 over 3. But instantaneous rate of change is a little bit more complicated than average rate of change. If I want to find an instantaneous rate of change, let's say that I want the time, or the instantaneous rate of change at time 2. Well, at time 2, how much does my distance change, my position change? Well, if I'm looking right at time 2, my position doesn't change at all because I'm frozen, stuck in time. So my position would change 0. And similarly, my time would change by 0. You can see that this would be potentially a problem because 0 divided by 0 is undefined. And if that's the case, then even though we know that this person is traveling 20 over 3 meters per second, we just figured out that they were traveling an undefined rate, which is not true. This is wrong. And so we can't just always rely on simple mathematics in order to find an instantaneous velocity. Instantaneous velocity can be a little bit more complicated than that. What we can do is find the rate of change from, say, 2 to 2.1 or 2 to 2.01 and use that as a way of estimating. And let me give you another example. Let's say that we're again dealing with position versus time. And so we'll say that this is time represented in seconds. And this actually would be represented by your position, which we'll call P, that's a good one, is equal to T squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, etc. If I wanted to find the average rate of change from 0 seconds to 5 seconds, the average rate of change would be represented by the slope of this line, which we would actually call a secant line, which is a term from trigonometry and geometry. A secant line connects 2 points. If I wanted the average rate of change, we could say that I have a change in position of 25 minus 0 over a change in time of 5 minus 0, because I'm going from the point 0, 0 to the point 5, 25, in which case I would have 25 over 5, which is 5 meters per second. Now the question then should be asked, does that mean that I'm always going 5 meters per second? No. In this first second, I only travel 1 meter. And then at time 2, I'm only at 4 meters. At time 3, I'm at 9 meters. So there, I've traveled a total of 5 meters in that second, but was I traveling 5 meters per second for that entire time? Let's say that I wanted to know the instantaneous rate of change, specifically at time 4. That is, I wanted to know what is the slope of the line right here. Now, if I want to know the slope of the line right here, this line that I've drawn right here is what we call a tangent line, which is an extremely important term in calculus. The tangent line is a line that is parallel to a curve at specifically one spot. I have a parabola that's coming up this way, and then I have a tangent line which for one instant of time is perfectly parallel to this curve. Now, I can't use my little trick that I dealt with up here because my velocity isn't constant. I'm speeding up here. So I want to know how fast I'm going in this spot, but I can't just say that my average rate of change is equal to my instantaneous rate of change. I have to get a little bit clever. So I know that I can't find the instantaneous rate of change by taking the position change at 4 minus the time change at 4, because the position change is 0 and the time change is 0. And again, I'd get that 0 over 0 thing. But what if I wanted to find from 4 to 4.1? Well, I could take 4.1 squared, because that's how I get my position, minus 4 squared divided by 4.1 minus 4. 4.1 squared, the reason that I'm taking 4.1 squared is this is my amount of time, and I am squaring it to get my position. This is essentially a y value, and this is essentially a y value. So if I were to take 4.1 squared minus 4 squared, I would get 0.81. That is my current change in y. And 4.1 minus 4 is obviously going to be 0.1. If I take 0.81 divided by 0.1, that's the same as really multiplying by 10, I would get 8.1. But this isn't actually my instantaneous velocity. This is an approximation of my instantaneous velocity. And so what I'm going to do is I'm going to make this 4.1 get closer and closer and closer to 4. Basically, I'm taking 2 points and I'm finding an average rate of change as those points get closer and closer together. The closer I make these points, the more accurate my approximation. So let's say instead of going from 4 to 4.1, I go from 4 to 4.01. Now, if I take 4.01 I get 0.0801 over 0.01. Well, that would be equal to 8.01. And if I made this go even closer, this number would get even closer to a number. And what number do you suppose this is getting closer and closer and closer to? That number is 8. And so we could say that my instantaneous velocity at t equals 4 is equal to 8 meters per second. So you note that my average rate of change was 5 meters per second. That doesn't mean I'm always going 5 meters per second. It means that if I take the average of all of my rates, I'm going 5 meters per second. At some times I'm going faster than that. At some times I'm going slower than that. This is a situation where I'm going faster than that. And my velocity is going to continue to increase as time goes on. I'll be going faster at this point than I was at this point. And I'm going faster at this point than I was at this point. This is a function that is continuously increasing in its velocity. I was able to find the instantaneous velocity by taking the limit of this sort of slope function as I made 4.1 get closer and closer and closer to 4. When I talk about a limit, I'm talking about making a number get closer and closer and closer to a value without actually equaling it. Because as we established before, if I actually make it equal 4, I would get that 0 over 0 thing again, which is a problem. So this introduces one of the main ideas of calculus, which is that of a derivative. A derivative is what we use to find the slope of a curve. If I've got a curve, I can find the slope of that curve by using calculus. And that allows me to find out how fast something is going, even if it's not going at a continuous speed. Think about accelerating on the freeway. You speed up and speed up and speed up. But what speed are you going at any given instant? You can't figure that out based on an average rate of change. You figure that out based off of an instantaneous rate of change. And that is what calculus is all about. Hopefully that helps people out a little bit and introduces you a little to the concepts we're going to be talking about this week. I will be posting another video shortly, which will get into a little bit more complicated concepts. But be well, everyone, and I will see you again soon. Bye.